Welcome back. Let us continue our discussion on IoT applications. So let us see our applications in industry domain. Here we have two applications. Uh, Machine diagnosis and prognosis and indoor air quality monitoring. Let us see the applications one by one. Machine diagnosis and prognosis. In the previous class, I explained you clearly about diagnosis and prognosis. Once again, I can explain you, right? So if this is the point where the machine has broke down, machine broke down, right? So I'll prefer different color, right? This is the timeline at this point of time, right? Fault, machine fault or broke down, right? If this is the time, so whatever the actions that we take here before the machine has broke down or fault, we are going to call it as a prognosis. After fault, if we are finding the cause of fault, we call it as a diagnosis. Right? In prognosis, right? The twist here is before the machine goes fault, we take necessary actions so that the machine does not go fault, right? So in the previous slide I explained it clearly, you can check it out, right? Highlighter. Right. Let us see the problems. Industry machines often face unexpected faults and there is a degradation in the performance. Degradation in the performance. This is one problem. Second problem is traditional maintenance is reactive. Reactive in the sense, right? So only when we observe the fault in the machine, then only we start repairing. Initially, we won't take any precautions. That is reactive approach, leading to downtime and high repair cost. See, downtime is the time during which the machine is not working. That time we are going to call it as a downtime. Down, machine is down, and that time. And see, once the machine goes fault, when the machine breaks down, then repair cost goes high. Repair cost goes high. Now, if we take care of the machine, we take necessary actions before the machine breakdowns, machine faults. In such scenarios, the repair costs are less. Generally, this happens. Right now, massive amounts of sensor data are generated in milliseconds, 2 seconds. Making analysis of such data is impractical. Right? It is impractical. Now, in many cases, it is difficult to establish precise mathematical models for machine behavior. We cannot make a precise mathematical model about the machine behavior. So, what are the solutions? Now, solutions are two: machine diagnosis, machine prognosis, and machine diagnosis. In machine prognosis, what I do? I predict the machine performance. Predict in the sense in advance. In advance, right? By analyzing the deviations from normal operating conditions, right? Normal operating conditions. See, for example, in the previous class, in transport system, in logistics, I have given you the example, right? There, suppose vibrations of the machine level, we are measuring the vibration of the machine with respect to the time. I found that vibration is constant. Vibration is constant. Now, suddenly, if the vibration of the machine increases with respect to the time, this we are going to call it as a deviation. This we are going to call it as a deviation from normal operating condition. Here I have given the example of measuring vibration. We can measure several parameters about the performance of the machine. It could be temperature of the machine or any other parameter. Now, machine diagnosis. Right, yes, once I measure the parameter, once it is deviating, I can think that something fault is in the machine, so that I can address that issue as early as possible before it breaks down and to reduce the downtime. Right, now what is this diagnosis? Now once the machine is broken down, this determines the cause of the faults in the machine. Yes, in several situations we go for diagnosis, in several situations we go for machines, it depending upon the application. Now, what is the role of IoT sensors? These monitors parameters such as temperature, vibration and other operating conditions. Just now I said, right, we measure any of the suitable parameters for that particular applications. Now, case-based reasoning, CBR, what is this? Uses this case-based reasoning uses past experience to solve the new problems, making it effective where mathematical model is difficult. See, in certain scenarios, I cannot derive a mathematical model. So in such scenarios, what I have to do? I have to use the past experience to solve a problem. A problem has occurred for this particular machine. I cannot make a mathematical model. In such scenarios, I will use the past experience. So let us see how it works. First of all, yes, in every application, IoT application, first we collect the sensor data. Sensors capture real-time measurements. Using temperature sensor, I will measure the temperature. Using vibration sensor, I will measure the vibration. Right. Using various other sensors, I will use measure RPM, revolution per minute, at very short intervals. Even I can decide the intervals. It is customizable. The interval in which we want to measure the readings, I can customize it, right, for every 1 second, for 2 seconds, depending upon the applications. Now, once I collect the data, I go for data analysis. Here, the algorithms compare the current data with baseline operating profiles to detect the anomalies, right? Outliers. Anomalies means outliers, right? Suddenly, the temperature I am measuring. I am measuring the temperature with respect to the time. Like this, the temperature is constant. Suddenly, one temperature point is here, one temperature point is here, one temperature. These are called as anomalies, outliers. So, when I monitor continuously, I can detect these anomalies. After this, I will do diagnosis. So, faults are identified by analyzing the deviations and correlating with the known issues. This is diagnosis. Prognosis. What do we do? Predictive models estimate the future machine performance and potential failures. Okay, so prognosis, I have given you the core idea of the prognosis. In prognosis, what we do? Right, generally we predict based on a present parameter, deviation of a parameter which I am measuring now. I will estimate, I will predict that this is going to be failure. Case-based reasoning, right, stores the past cases of machine faults and resolutions, right. In a previously, some 6 months back, from 1 year back, there was a fault in the machine. So when there is a fault in the machine, I opened it and I made a diagnosis. I diagnosed it and I find out the causes. I found out the reasons that I have noted down, right. So once I note it down, then past I check, yeah, past in the history, this was the problem of the machine. Now, so all those cases I will check and I will find out, right, the fault. What is the fault? So this is the cause-based reasonings. What does here we do? We match new problems. We match the new problems with similar past cases. Similar past cases. And based on that, we suggest the solutions based on the historical incomes. We suggest the solutions based on the historical outcomes. Now, benefits. Yes, reduced downtime, early detection and prediction prevent unaccepted breakdowns. Cost savings, optimizes maintenance schedules and reduce repair costs, right? So optimizes maintenance schedule means what? I will schedule that for every 6 months once I have to do the complete checkup of the machine, or every 3 months I have to do. I can optimize. If I have data, I have optimize, and I will prescribe that your machine has to be serviced or maintained for 6 months. Every 3 months you have to do the machine servicing. Reliability. Reliability means trust, improves machine performance and operation stability. Scalability, the whole system, right? It can handle massive sensor data streams efficiently. Flexibility, this continuous based reasoning provides a solution even when mathematical models are unavailable. Just now we have discussed about this case based reasoning, right, where the mathematical models we cannot make, we cannot derive the mathematical model. In such scenarios I have noted down the past faults, past problems of the machine. Now whenever a new problem has occurred, I compare with the past problem and then I found out the reason. Safety, prevents accidents by addressing the fault proactively. Sometimes what happens in industrial level, because of the fault of the machine, a human being may suffer. A human being, right, may meet with the accident and lose his life. So now if we have some problem, if we have addressed the fault proactively means before it has occurred, I can save the lives of the human beings. So now let us move to the another application of IoT in industry, that is air quality monitoring. Air quality monitoring. What is the problem here? Harmful gases. Which are those harmful gases? Carbon monoxide, nitrogen monoxide, nitrogen dioxide can cause serious health problem for the workers who are working in the industry. Traditional monitoring methods are limited and may fail to detect these gases, the concentration of these hazardous gases in time. Hazardous gases are those gases which are harmful for human beings, which are harmful for the life of living beings. So traditionally I cannot monitor them. Manually I cannot monitor continuously. Now in certain scenarios what happens? Indoor. Here we have word indoor means closed environment. The industries are closed in a building. So in such scenarios, poor ventilation means air is not flowing inside the building, and undetected toxic zones increase risks of accidents, illness and reduced productivity. When there is no proper ventilation, when there is no proper airflow, the toxic gases may accumulate inside the building. Sometimes the human being may become less productive. What are the solutions then? Now I will design and implement IoT based monitoring systems. What they do? They use specialized sensors to continuously track indoor air quality. These systems can be deployed across multiple locations within the facility for comprehensive coverage. In the sense, these systems I will employ them, I will deploy them, I will place them in multiple locations within the building, right? Within a building, if in a single floor, if it is very large, right, in four corners, in the middle I will place the system. If the building is 2 floor, I will place these systems in the second floor also, right? Now wireless sensor networks identify hazardous zones and trigger corrective measures such as ventilations or alarm. Okay, so this system will identify the hazardous zones where the gas is accumulating, where the gases are leaking, and trigger measures. Which are those corrective measures? Either I will go for proper ventilation. Ventilation means like I will go for exhaust fans, right? So proper exhaust fans or proper, right, we'll go for proper exhaust fans, the fans which suck the air in from inside the building, and they will throw the these gases, harmful gases, out of the building. Or I will raise the alarm. right? I have alarm machine which will start beeping so that the human beings who are working in the factory get alerts and they can evacuate the building. They can go outside the building. Real-time data is transmitted to the centralized servers or cloud platforms for analysis and decision making. So let us see how it works. I have gas sensors which detects the concentration of harmful gases, that is carbon monoxide, nitrogen oxide, etc. in the environment. I have wireless sensor networks. These I will have the setup of a wireless sensor networks. We connect multiple IoT devices across different locations to provide the full coverage. These now once the sensors wireless sensor networks collect the data, these readings are sent to the clouds for storage and analysis. Now I will do the analysis of these data. So algorithm detects the unsafe levels and generates alerts for immediate corrective action such as evacuation, right? Corrective measures. Automated systems activate the ventilation. They give the signal to the alarm or send evacuation protocols to ensure safety. Benefits. One of the important benefit is worker safety. Protects the employees from exposure to the toxic gases. Real-time monitoring. Continuous tracking ensures immediate detection of the hazardous gas because I am in the real time I am continuously tracking, right? So immediately I can detect the dangerous level of the gases. Efficiency. Automated alerts reduce the reliance on manual inspections. When compared to manual inspections, the automated alerts reduce. We can trust the automated alerts more because they are doing it continuously. When the systems are doing it, there is a less probability that there is a error. Preventive actions. So here we are identifying the hazardous zone early, enabling corrective measures before the accident occurs. So we are taking all these actions before the accident occurs. Hence the name preventive. Scalability can be deployed across multiple facilities or even in large industries. See, whenever there is a scalability word, it means it is large. Scale up means increasing the size. Increase the size. Compliance helps meet occupational health and as whatever the government makes safety and health regulations, accordingly we can compliance uh, or compliance means according to those rules we are implementing all the facilities according to the rules and regulations made by the government. This is called as compliance. In the simple words, compliance means obeying, right? Is it clear? Okay. These are the two applications of the IoT in industry. One is indoor air quality monitoring, another one is machine diagnosis and prognosis. Alright. So these are the applications. Let us end this class here.